All right. So intro to exponents and logarithms. Okay. So we'll kind of, like I said, review some, review some intro or some properties of logarithms and stuff like that. Then we'll also get into like graphing exponential functions, just like sketching the graphs again. You may remember doing it a particular way with algebra 2 and stuff like that. Mine might be slightly different, but hopefully easier than that. Okay, and then we'll, like I said, we'll do the logarithm. We'll talk about logarithms too. So, yeah, okay. And I'll just kind of introduce exponent properties maybe in a little bit different way than you're used to seeing. Okay, I'm not going to jump right into the property itself, but kind of maybe help us see with the pattern and stuff like that. So when we see something like 2, and we see that little 3 superscript, right? What does that mean to do? What does that tell us to do? What is it? Right, okay, so this thing that's being raised to the third power, you take that thing and you multiply it by itself 3 times. So 2 times 2 times 2, which is 8. Okay, right? And so then when we see something like 2 to the second, we know that's going to be just 2 times 2, which is 4. And then 2 to the 1 is just, well, 2, right? Because there's just 1, 2. Right? And so using this idea, this also helps us to extend into like, well, something like 2 to the 0. Because now that definition of multiplying 2 by itself a certain number of times, well, how do you multiply something by itself 0 number of times, right? So that doesn't really quite work here, but we can still like kind of use at least the pattern that we see here, right? Where if we go from 2 to the third down to 2 to the 2, right? The answer for 2 to the third is 8. The answer for 2 to the 2 is 4, or the value, I guess I should say there. And to get from 8 to 4, well, what kind of mathematical thing could we do? Half of it, right? Or divide by 2. And so does that pattern still continue when we go from 4 to 2? Is that the same pattern? Half of it or dividing by 2? Yeah, it does, right? So every time we go down one exponent, it seems like we're dividing an additional 2 out. And so then when we get to that 2 to the 0, it would make sense then to continue that pattern and say, okay, well, to go from 2 to the 1 to 2 to the 0, we should divide further by a 2. And what's 2 divided by 2? 1, right? And so 2 to the 0th power is 1, right? That is the definition of anything to the 0th power, except for 0 to the 0th power. That's an indeterminate form. But 1 to the 0, pi to the 0, e to the 0, 2 to the 0, that's all going to be 1. Right? We can extend this pattern even further than this idea when we talk about negative exponents, right? So for example, 2 to the negative 1, it's 1 less than 0, and so we should, again, extend this pattern one more step. We'll multiply by 1/2 or divide by 2, and 1 times 1/2 or divided by 2 gives us 1/2, or as we sometimes also think it, 1 over 2 to the positive 1. Right? And then 2 to the negative 2, we'll do one more here. And then we'll move on, okay? 2 to the negative 2, well, what's 1/2 divided further by 2? 1/4, right? Or 1 over 2 to the positive 2 like that. Okay? So I know that exponents can sometimes get a little confusing, right? A little bit tricky, but maybe this is a different way to think about it to help you kind of remember, what to do with negative exponents and things, right? So this idea here of 2 to the negative 1, right? You maybe know, like, oh, we're supposed to move it to the denominator. But the real idea here is that we're taking, we're just dividing by a 2, and that's what moves it to the denominator. And then dividing that by a further 2 gets us that 1/4 of the 1 over 2 to the positive 2 there, like that. Okay? And of course, there are other properties we should be familiar with, right? So let me just summarize some of these bigger properties too. For example, if we have like 2 to the 3rd times 2 to the 4th, what does that equal? What's that same as? 2 to the what? 2 to the 7th, right? Because, again, using our basic definition of exponents here, if I have 2 to the 3rd, that's 2 times 2 times 2. and I multiply that by 2 to the 4th, which is 2 times 2 times 2 times 2, like that, well, it's all multiplication here, so I can just see, well, there's 7 2s, so it gives me 2 to the 7th, right? I mean, it's pretty straightforward there. Likewise, if I take 2 to the 3rd and raise it to the 4th power, okay, well, that's 2 to the 3rd times 2 to the 3rd times 2 to the 3rd times 2 to the 3rd, right, which is 3 plus 3, 6 plus 3, 9 plus 3, 12. It's, yeah, 2 to the 12th. Okay, but of course, what's the shortcut we can take to get from here to here? Multiply the powers, right? When you have a power raised to a power, you're multiplying there because of that repeated multiplication. Okay? And then, of course, we can divide too, right? So if we have 2 to the 4th divided by 2 to the 3rd, what is that going to equal? 2 to the 1st, or just 2, right? And again, the idea here, well, let's expand it out, right? 2 times 2 times 2 times 2 over 2 times 2 times 2. Those cancel, and you're left with just 2 over 1, or 2 to the 1, which is, again, 4 take away 3, right? 4 take away 3 gives you that 2 to the 1st power there. Okay? So, let's try. So some things we should be able to do. For example, we should be able to simplify exponents, okay? Things with exponents. So I'm going to keep with the 2's here. 2 to the negative 9 over 2 to the negative 7 times 2 to the negative 5. And again, you have like a couple paths you can take here. There's not just one way to do this, and I think that can cause some trouble for students, I guess, okay, about when you can't do certain paths. But there are a couple of different ways you could go here, okay? Intuitively, what do you want to maybe do here for the first step? So Megan, what do you say?
Like flip the numerator and the denominator.
Okay, so you don't like having negatives in your answer, in your problem, I guess, like that. So any negatives that are in the denominator, move to the numerator. Any negatives in the numerator, move to the denominator. Okay, so we can do that. So that would become then 2 to the 7th times 2 to the 5th over 2 to the 9th, like this then, right? Okay, and in this case, since all the exponents were negative, the fraction like essentially just flips, right? Okay. So following this path, what might be a next step for us to do here then? Okay, right. So, but what would that entail? What would we need to do still? Okay, 2 to the 7th times 2 to the 5th. So that would become 2 to the what?
2 to the
12th, right? We add the exponents there because we're multiplying the base numbers. Okay? And now how can we simplify from here? Julie?
Minus the 9 from the 12 since when it's on the bottom you minus it.
Right, we got division. Right, we got division, so we can subtract them. So yeah, 2 to the 3rd. Or alternatively, yeah, and I don't know if you meant to say it this way, but the way you were saying it, it's kind of like we could rewrite 2 to the 12th over 2 to the 9th as 2 to the 12th times 2 to the negative 9, right? We can move that 2 to the 9th up into the numerator by giving the opposite sign there, and then we add the exponents 12 and the negative 9 make a 3 as well. So that's the other option, which again we know is just finally 8. I guess you could just say that's your final answer, 8. But 2 to the 3rd is acceptable, I guess, too. Okay. Now, did anyone have a different thought about how we can maybe start this here? Did everyone think we should just flip it, or did everyone have a different idea about how we could have gone there? Okay, yeah, Cooper?
What if you just found 2 to the 7th and multiplied that by 2 to the 5th?
So, I mean, right, we could combine these two together as they're currently written, okay? Or I think maybe this is what you're trying to say, I'm not sure, but...
I'm talking about the second part.
Oh, okay.
Why can't you just solve it right there?
Like use your okay, I see what you're saying. Get this, times this, and then all over that. Yeah, you could. That would work, yeah, you could. I was saying, well, we can combine straight ahead in the denominator, right? We don't need to rewrite the negatives. So 2 to the negative 7 times 2 to the negative 5, you just add them up, you get 2 to the negative 12. Okay? And then it'll be negative 9 divide, so minus a negative 12. And so I'll write it out maybe more explicitly here, like that, right? But minus negative is really plus positive. Negative 9 plus 12 does give us 2 to the 2 to the 3rd, like that. Okay, which is just 8. I think I hooked you. There you go. Thank you. All right, so anyway, actually don't use that anyway. But anyway. All right, so let's have you guys try one. All right, so a over b squared, that quantity to the negative 2, times a squared over b to the third. Okay, simplify that as much as you can. Okay, simplify, simplify, give it a try. And I will do the same. What is that number? Oh, I see. Yeah, you flip it, but then you also square it too. So it should be over 8 squared. Try to end no negative exponents. So write it down. Yeah, that's right.
I'm gonna go like this. Can I do that?
Yep.
Oh, no, I don't mean it as negative. Okay, well,
So
negative 4 plus
A was also squared. So A for n, and you can pull that 2 out. Like, both here. Same thing for 3. Okay. Give you 30 more seconds. Okay. A to the 4, B to the 1. Final answer. Or just A to the 4th B, too, if you like that. Because, of course, B to the 1 is the same as just B, right? We assume an exponent to the 1. Questions on any of this? You might have chosen to go a slightly different route than I did, okay? Again, there's different ways to go. I distributed the negative 2 and distributed the 3 kind of there, and then I multiplied across the top, and then, you know, the B was the negative 1, so I moved up the numerator like that. Okay. Lots of different ways to think about it, so, you know, yours might not be the same.
You have to write B to the 1, or could you just write B?
You write just B, that's fine. It's understood there, right? Okay. Other questions on any of that? Anyone need me to walk through it or see if they'd like try something a different way? I can also like try and describe it that way too. No? We're all good there? All right. Let's continue on then. So that's just your like little quick refresher on exponent properties. We'll now move into looking at the graphs of exponential functions too. Okay? And there's kind of like two styles of exponential functions with which we need to be familiar. All right. So the first one we'll look at here is exponential functions of the form f of x equals a times b to the x. So first of all, just to pause real quick here, this is an exponential function, right? The two forms are going to come right here. So here's the first form, b not equal to 1, b greater than 0. Okay, so an exponential function, first of all, just in general, b will not be equal to 1. Okay, now, let's think about this. Why do we have to say that b doesn't equal 1 here for an exponential function? Think about what would happen if b was 1, okay, and what the graph of this thing would look like. All right, Megan, you want to say something?
Well, it would just be like a horizontal line or like a linear function.
So, yeah, if b is 1, we're going to take 1 and raise it to the x power. So as our x is changing, right, as we move left or right on the x-axis, x will change. But if you take 1 and raise it to any power, what are you going to end up with? 1, even a negative power, right? Like 1 to the negative 2 is 1 over 1 squared, which is still 1, so it's 1 over 1, 1. Okay? So in other words, as Megan was saying, it's always going to be a. Okay? You're going to have just a horizontal line of a. And that's not really an exponential function. That's well, what is a horizontal line? It's a linear function, right? So we wouldn't want b to be equal to 1. Okay? Also, we want b has to be greater than 0, because if b were negative, well, that would cause some really interesting, well, actually, never mind. We'll see what happens here with b being negative in a second, I think. Yes, yes. So why do we have to stipulate that b is going to be greater than 0? What kind of issues we run into if b were, well, not greater than 0? What kind of issues we run into? Yeah, Parker?
It'd be negative and then positive and negative again, like for when x goes to even or odd exponent.
That's true, right? So let's think about this. So let's pick a number like -2, something familiar, right? That's not greater than 0, right? That's breaking this rule. What happens? Well, if we put a -2 in here, we'd be raising -2. Sometimes -2 would be positive, right? -2 to the 2 is positive, but the -2 to the 3 would be negative. So our function would be like kind of jumping y values potentially, okay? But also think about it this way. Are we only plugging in whole numbers for x? Did we stipulate here that x had to be whole number powers? No. So for example, we could put like 1/2 in for x. And if we try to do if we try to do like -2 to the 1/2 power, what's that going to be? Square root of a negative, imaginary, right? And so we end up with imaginary values in a function that also has like real values mixed in, and so it's going to create like a weird looking function. I think, and I don't even think, let me see here, I don't think the graphing calculator will let you do it. I'm going to try here real quick, but I don't think it does. I think it says error, or it doesn't graph it at all. Yeah, okay, it doesn't graph it at all. So there you go. All right, it won't work. Okay, so we're going to look at first at cases, because there's two different cases then that arise out of these stipulations. We're going to look at first at cases where b is greater than 1. Okay, cases where b is greater than 1, and we'll just do an example here of f of x equals 3 to the x power. Okay, so a in this case would be what number? Well, maybe I should ask an easier question. What's b going to be in this case? The 3, right? B is the part that's being raised to the x power, so 3 to the x. So what is a then in this problem? Not 0, because 0 would give us a 0. It would have to be 1. So a can be 1. That's no problem. In this case, a is 1, right? So you could think of it maybe in a more formal sense as like, like this. 1 times 3 to the x, where the 3 is the b, the 1 is the a, and of course then, well, exponential makes x. Okay? So let's make a little table here, just to kind of get an idea about what's going on. And I'll pick some small values for x here because these things get out of control real quick because of the exponential growth. Let me see. Okay. So let's see here. Let's start with 0, right? So what is 1 times 3 to the 0? What's 3 to the 0? 1, so it's going to be 1. Okay. How about 3 to the 1? 3, right? 3 to the 1 is 3 times 1, so it just gives us 3. Okay, how about 3 to the 2? 9 times 1 will give us 9. 3 to the 3? 27 times 1 is 27. 3 to the negative 1? 1/3, right? 1 over 3 to the 1. And then how about 3 to the negative 2? 1/9, or 1 over 3 squared, right? So 1/9, yeah, okay? So there are our points. Let's sketch this out. Okay, so 1, 2, 3. And then, goodness, we have to go from 1/9 up to 27. So I guess I'll count by 5s on my y-axis. 5, 10, 15, 20, 25. Okay. I think I'll count by 1s on my x-axis. So your x and y axes, they can have different scales, right? But your x-axis must be all one scale. Your y-axis must all be the same scale too. So, all right, let's plot these points then. So let's see here. So 0, 1. Well, here's 0, and I'm going to put 1, I don't know, like right there. And then 1, 3. 1, 3, so 3 will be a little bit higher. And then 2, 9. So 2, there's 5, there's 10. So 9 will be just beneath that. And then 3, 27, there's 3, and then 25, but a little bit higher than 27 will see you right there. And then negative 1, 1/3, well, I'm just going to kind of like, that's not going to be, we'll do the best we can there, I guess. Okay, if we connect these dots, we get a curve that looks like this. Okay, and so now that we have introduced this function, well, reintroduced this function to you guys, right, since you've seen it back in Algebra 2, let's talk about some of the characteristics again, right? So we can talk about, for example, its domain. What would its domain be? Negative infinity to infinity. Okay, very good, or all real numbers if you like. What about its range? What does it look like the range is going to be? So yeah, excluding 0, so exclude 0 to exclude infinity, yeah. 0 to infinity, not including either endpoint, of course, there, yeah. Okay, we'll never actually get to 0. We'll get close to it, but we'll never actually get there. Okay. So with that being our range, what can we say about our x-intercepts? There won't be any, right? There won't be any. Because the range, we never get to the y-axis. We never actually hit the y-axis. Okay. Now, if we transform this function, right, if we shift it up or down, then it could intersect the y-axis. Okay. And what about y-intercepts for this function? 1, right? 0, 1 is our y-intercept, right, where the graph crosses the y-axis there. Okay. Let's see here. Do we expect to see any vertical asymptotes here? So, right, no, we don't. Now, you might say, but Mr. Wiedemeyer, look, this is like curving up. It's curving up like maybe there's some vertical asymptote over here that's just going to keep growing. But the idea is no, right? It's just increasing at this rate. But you can plug in any x value on this axis, right? You can raise 3 to any number you want, okay, any real number you want, and you'll get an answer, all right? So there's no issues here. There's no, discontinuities with this thing. What's the end behavior here? We could say as x approaches infinity, so as x approaches positive infinity here, what would f of x approach? Positive infinity as well. As x approaches negative infinity, what would f of x approach? 0. Okay? So that would indicate a horizontal asymptote where? 0. Okay? So we're going to have a horizontal asymptote here. The left behavior, right, approaches a number. It is limited. The right behavior, though, the right end, right end behavior there, does not have a limit, though. Okay? It is infinite. It goes on forever. Okay? So this is a different kind of function than what we've maybe experienced so far. All right. Make sure there's anything else. What kind of behavior will we describe this function as exhibiting? Like, so for example, is this function constant anywhere? Does it look like this function will be constant anywhere? Yeah, no, it doesn't look like it, right? Does it look like this function is decreasing anywhere? From left to right, does it look like it's decreasing? No. What about increasing? Yes, okay. And in fact, what we know, this function will be increasing where? Everywhere. Okay, everywhere this function is increasing. Okay? So therefore, we would expect its derivative to always be positive, because all the slopes here, right, are going to be positive slopes to indicate that increasing. So the derivative of this thing, we'd expect to always be positive. Okay, always be positive. Okay? Again, that's some more calculus stuff, but anyway. Okay. Let's have you guys try one here then. Okay. So now we'll look at cases. So we looked at cases where b is greater than 1, and now we're going to look for cases where 0 is less than b is less than 1. Again, remember, b cannot be 1. It won't be exponential anymore. Okay. But there's a different kind of shape that we get when we experience this. So, and now we're going to use 1/3 instead of 3 here. Okay. So I'll start a table here. You guys go ahead and fill it out, and then plot these points. Well, I already gave you one. Mr. Witt's getting ahead of himself here. 1, 2, like that. Okay, so I gave you a freebie. All right, so go ahead and finish that table off, and then plot those points on a little sketch like we just did. Question? Yes, go ahead. Okay, like one more minute here, one more minute. Okay. Should look something like that. Okay. What's the domain of this graph? All real numbers again, negative infinity to infinity. Okay, what's the range of this graph? 0 to infinity again. Okay, be careful here though, because when you do that 0 to infinity, right, you look at the top, the highest one that is, and you can't see. You start at the highest. You might think, oh, we go infinity to 0. No, it's 0 to infinity. Okay. All right. In fact, does anyone recognize, or can anyone say, maybe anyone have an idea about a maybe more specific kind of relationship to the graph that we just saw? What does it look like, maybe? Flipped over the y-axis. Yes, it is a reflection of the y-axis. Now, let's go back to our thinking about transformations a little bit here and see why that maybe is so. Okay, so let's just take if f of x here is equal to 3 to the x. Okay, forgive me for overusing this 3 to the x here again, but why not, since that's what we just talked about. All right, so if we have that, and we see something like g of x equals 3 to the x plus 1, like this. Okay, 3 to the x and then plus 1. What kind of transformation will we expect from this? What will this do? What does this do compared to our 3 to the x there? Up 1, thank you, exactly right. Shift up 1. So then the range for this will not be 0 to infinity, it'll be, sorry, this one will be 1 to infinity, right? 1 to infinity, right? All right, how about g of x equal to 3 to the x minus 2 and the exponent like that? So the x minus 2, all in the exponent. What kind of transformation will we expect from this? Shift to the right 2, okay? And this is because our number, our value there is up with the x. So shift right 2. Okay, so again, you guys can get the idea how to more generally apply that, right? Okay, if we take that 3 to the x and put a negative in front, so negative, the parentheses, 3 to the x like that, what kind of transformation would that result? Reflect over the x-axis. And if we want to reflect over the y-axis, then I would need to write g of x equals 3 to the negative x like that. Okay, that is a reflection over the y-axis. Okay, but now wait a minute. We just saw that 3 to the x and 1/3 to the x, they look like reflections of each other over the y-axis. Well, 3 to the negative x, isn't that the same thing as 3 to the negative 1 times x? Right? Negative x is negative 1 times x. And we know from our properties of exponents that when you have two powers multiplied together, that can result from a power raised to a power, right? So this, I know this is backwards, right? So that's maybe a little more uncomfortable, but this is true, right? If I were to remultiply, if I were, power to a power, if I were to remultiply these, I would get this, right? But what is 3 to the negative 1 the same as? 1 over 3, or 1/3 to the x. Okay? And so there you see it, right? 1/3 to the x, okay, is the same thing as 3 to the negative x. And so we end up, that is exactly what 1/3 to the x is. It is the reflection over the y-axis of 3 to the x, okay, because of that result there. Alrighty? Questions on that? Okay, and of course these things apply, to 2 to the x, 4 to the x, 5 to the x, e to the x, pi to the x, if you like. Okay, but yeah. Questions on any of that? Alrighty, so that's all for exponentials, but now let's talk about logarithms some, because we can't talk about a function or new functions without also talking about those functions' inverses. Okay, so logarithms. Here we go. Let's see here. Make sure I do this right. Okay. So, like I've said in the past, okay, I'll say it again here, right? Typically in math, we tend to, the pattern seems to be, right, in math, is that we learn a function, and then eventually we learn about the inverse of that function, or how to kind of like undo that thing, right? How to cancel it out, all right? So, having spoken about, squaring, right, x squared, we then learn about the square root of x, right? Or, when you learned about addition, you later learned about subtraction. When you learned about multiplication, you later learned about division, right, after that. And so here with exponential functions, we now are going to talk about logarithms, which you can think of as being like the inverses of exponents. Okay, they kind of like eliminate exponents. That's one way you can think about it. Okay. A logarithm allows us to take something that's in exponential form. For example, here, y equals a to the x. This is like an equation in exponential form. And then we can rewrite it using this idea of a logarithm, okay, that you guys learned about in Algebra 2. All right, and so the base of our exponent, okay, so this is a, base is a, the power is x. The base becomes the base of our logarithm. So it's log base a of y equals x. Okay, and then we get our equivalent logarithmic form. These two statements, these two equations are saying the exact same thing. The exact same relationship, just in two different ways of showing it. Okay, and this again is how you would read this as log base a of y equals x. Okay, log base a of y equals x. So let's see some examples of how we're going to use this idea of exponential form or logarithmic form. Okay, and our directions here are going to just be evaluate, or you could say simplify, I guess, if you like, one of the two. So let's say, for example, we wanted to simplify log base 2 of 8. Okay, let's say, for example, here we want to simplify log base 2 of 8. Okay, anyone know what this is off the top of their head? 3, yeah, 3, okay, good, yeah, if you got 3, that's right, it will be 3, okay. If you didn't get it, that's okay. I'll show you here how to do that. All right. So, you might be a little confused because I've got log base 2 of 8, but in what I just showed you here, there's log, there's our, so 2 would be like in the A's spot, 8 would be in like the spot for the Y, but I don't have an equation here. Okay, there's no equals. But I'm going to just throw it in here because what are we trying to do? We're trying to see what does this thing equal. So I'm going to say, well, let's just say it equals some unknown value. We know it's going to be 3, right? But let's just say it's going to be some unknown value. Let's just say it's equal to x. Okay, so I'm going to take log base 2 of 8. Let's say, let's set this equal to x. Okay? And so then I know, okay, so this is a logarithmic form I have. I can rewrite, by rearranging the numbers, I can rewrite it back into an exponential form here. So this base a, this a is going to be raised to the x power. So in other words, my base here, 2, gets raised to the x, 2 to the x. And that equals, well, y over here on the other side. Okay, I can flip it around, I guess, right there. It should be 8 equals 2 to the x, I guess, but you get the idea. And so what is this really asking us? 2 to what power gives us 8? And what is the answer for that? Well, 3. And if you really don't believe me, 8 we know is 2 to the 3rd. We have 2 to the x equals 2 to the 3rd, so that means x has to equal 3, right? And so the answer there is 3. So in other words, log base 2 of 8 is 3. Okay, that's the answer. That's the value. Okay? So when you run across like a logarithm in the wild, right, if you see something like this, log base 2 of 8, okay, this is asking Okay. 2 to what power gives us 8? Okay? That is what a logarithm is asking. When you learned about square roots, right? We did the square root of 4. Okay? When you answer a square root question, you're asking, you're basically saying, what squared gives me, 4? We're going with the square root of 4. You're saying, what squared gives me 4? Well, you say 2, right? Or, well, negative 2, depending if you have an equation there or not, right? Same idea here. 2 to what power gives us 8? That's what that is asking. Okay, so I'm going to give you, oh wait, no, we'll do some together, and then I'll have you guys try some. So we'll say evaluate the following. Okay, so number 1. Okay. Log base 3 of 81. Log base 3 of 81. Or in other words, 3 to what power gives us 81? And what's the answer? 4. Yeah, 4. If you're not sure, just keep multiplying 3s. 3 times 3, 9 times 3, 27 times 3, 81, Okay. Alternatively, if you don't like that, you can take log base 3 of 81, be like, I don't know what it equals, I'll set it equal to x, rewrite in exponential form, 3 to the x equals 81 then. And then we see, aha, 81 is 3 to the 4th, so 3 to the x is 3 to the 4th. That means that x has to be a 4 there. Alternative. Okay, let's try another one. What's log base 3 of 1? Or in other words, 3 to what power gives us 1? 0. All right, how about log base 4 of 2? 4 to what power gives us 2? Ooh, yes, 1/2. 4 to the 1/2, right? The square root of 4 is 2. So 1/2 power is a square root there. All right, how about log base 10 of 1/100th? Sorry, I'm off the screen. There we go. Log base 10 of 1/100th. -2. Okay, and again, if that's like a little funky for you here, well, 1/100th is the same thing as 10 to the -2, right? So what power of 10 gives us 10 to the -2? Well, that's the -2 there. All right, let me give you 3 to try. Try log base 2 of 16. Log base 100 of 10. And log base x of x to the 5th. Nah, just 3.
Wait, what does the second one say?
Log base x of x to the 5th. All right, 30 more seconds. Okay, log base 2 of 16 is 4. Log base 100 of 10 is 1/2. Log base x of x to the 5th is 5, comma, x not equal to 0, right? Because if x is 0, then all bets are off there. But yeah.
For number 6, could you also put -2 or just 1/2?
So 100 to the -2, that'd be the same thing as then 1 over 100 squared, which wouldn't give us 10, right? So yeah, no, -2 wouldn't work there. You would need to have a 1/2. Okay, would need to have a 1/2. All right, other questions on that before we move on? Okay. By the way, real quick, I forgot to mention this, right? On the exponential stuff. Because of the way this curve is, right, we know it's increasing everywhere, so this is called exponential growth, right? Exponential growth. So when b is greater than 1, that's exponential growth. Forgot to write that, so I'm going to put that here. Exponential growth. Okay? And then here, this one, because our b is between 0 and 1, we would call this exponential decay. Okay? And different, things in nature experience exponential growth or exponential decay. So, yep, populations do, radioactive isotopes, those kind of things. So, okay. Right. A few other things to round out our logs. We'll graph one and then we'll be done here. Okay, so just a couple things to note. Log base 10 of something is called the common log. Okay. Also, on your calculators, you will not see log base 10 as a button. Log base 10 is the same thing as just log with no base written. Okay? So in other words, if you see log of 100, that's really log base 10 of 100, which is equal to what? 2. Okay? So if you type in your calculators log of 100, you get 2. Okay? We have another log that shows up on our calculators, and that is the natural log. Okay. And that is represented with log base e, the number e, okay, which I think we'll talk about more later, not right now. Okay. Log base e, or on your calculators, it's represented as ln, capital L, capital N on your calculators, but really, normally it's written with a cursive, like L and N, like that. Okay. From the French, logarithm naturel, kind of thing. Okay. All right. And then there are 3 basic properties with which we should be familiar, but they're not going to be like mind-blowing here. They'll just be like, oh yeah, that makes sense. Hopefully, at least. Okay, of logarithms. Okay, 3 properties. Property 1. Log base A of 1 will always equal what? 0, right? A to what power gives us 1? Got to be 0. Okay, again, A not equal to 1. I guess I should say A greater than 0. Yes, A greater than 0. We don't want it to be 0. Yeah. A greater than 0 there. Yep. A greater than 0. Okay. 2. Log base A of A is always going to equal what? In other words, A to what power will give us A? 1, right? Anything to the first power will give us itself. And then number 3, log base A of A to the x. X. Okay? And there you see that inverse property, right? Where we take an exponential, A to the x, we do the logarithm base A of A to the x. That cancels out the exponential and we're left with just x, right? There's that inverse idea where something cancels out another thing, right? We have an exponential, our variable's in the exponent. How do we get the variable out of the exponent? Use a logarithm with the same base, with a matching base. All right, last thing here. Since logarithms are inverses of one another, I'll do log base 3 of x. Since logarithms are inverses of exponentials, right? If you have a good idea about what an exponential function looks like, you should also have a good idea about what a logarithmic function should look like, okay? Graphically speaking, right, if two functions are inverses, how are they transformed? How are they transformed from one to the other in the plane, in the corner plane?
Reflection over y equals x.
Reflection of the diagonal line y equals x. So you can imagine, you know, in your brain, use your imagination, okay? If you have the line y equals x drawn here, which would be something more like this, okay, a very shallow line, you can imagine reflecting it over here, okay, and get an idea of what it's going to look like. So let's do that right now. Okay. Ugh. Well, I'm going to change this to 2 because otherwise the numbers are going to be just too big. All right, so we'll do log base 2. I know I'm breaking with all the 3's that I've been using, but so it goes. All right, so we'll start with x equal to, well, Can I start with x values like -2, for example, here? Can I find log base 2 of -2? Or in other words, can I evaluate 2 to what power gives me a -2? Can I raise 2 to a power and get a negative number? Yeah, the answer is no. Okay, so we cannot take the logarithm of negative values. All right, can't do negative. But what about 0? 2 to what power gives me 0? Can you raise a number to a power and get 0? No. So we won't be able to evaluate the logarithm of 0 or the logarithm of negative numbers here. All right. Well, I'm not going to do fractions. I'm going to skip right ahead to 1. What's log base 2 of 1 going to be? 0. What would be a good next number to pick here? 2. Okay, because 2 to what power gives me 2? 1. What would be a good next number to pick? Ooh, 3. Do you know what power of 2 gives me 3? Not easily, right? But if I pick 4, I know 2 to what power gives me 4? 2, right? And then I can pick 8 and get 3, and then you get the idea, so on and so forth. I could also, if you really want to be clever, you could do something like, for example, 1/2. 2 to what power gives us 1/2? -1. Okay. 2 to what power gives us 1/4? -2. Okay, so you can get negative y values here. Okay, so let's see what this is going to look like then. Ugh, I didn't graph that vertical the vertical axis very good. The y-axis very well, but oh well. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8. So we'll plot these points. So 1/2 -1, halfway -1 there. 1/4 -2, so like right there. And then 1, 0, and then 2, 1, and then 2, 3, 4, 2, and then 5, 6, 7, 8, 3. Okay. What would the domain be for this function? 0 to infinity. And what's the range going to be? -infinity to infinity. Oh my gosh, that's the exact opposite of our domain and range here. But wait a minute. We switched to x and y's to find inverses, right? And so it makes sense that the range of our original function will become the domain of the inverse, and the domain of the original function will become the range of our inverse, okay? So they flip-flop, exactly. Okay, even though these aren't exact inverses, but it'd be the same properties for the log base 2 and 2 to the x.
Isn't this the ones where they flip over the x equals y axis?
Yes, exactly right. Yes, that's what we see. Yep, exactly right. This is exactly what we see. You can see it here somewhat, If you graph, 2 to the x and you graph log base 2 of x in your calculator, you can see it that way too. what else I want to say here? Oh, right. Do we have any vertical asymptotes?
Yes.
Yes. Where?
0.
At 0, right? We expect a vertical asymptote there. Do we have any horizontal asymptotes here? Right. As x approaches infinity, f of x will approach what? Infinity. It's going to keep going. It's going to keep growing here, okay? Pretty slowly, right? It gets slower and slower as we go, right? But we are increasing everywhere. And so it will eventually go to infinity, okay? Very slowly, but it will. Okay. I think that's all I've got for you there, okay? So thank you guys for your patience. I know that was a lot, but thank you. We caught up a day. That was good. Useful. Your homework's posted in Google Classroom. All right, so I would take a look at that tonight. I'm not going to collect the homework from last week. I'm going to have you guys put the homework in with this week's homework. So that's why I said I'm not going to collect the homework from last week. I still know what I'm talking about. No, okay, good. Yeah, then yeah, that makes it easy for me. Okay. So yeah, you have another question?
Just my question. Are we also combining Thursday night and Wednesday night's homework for tomorrow night?
Potentially, I'm going to see if that's doable.
Okay.
I know, I'm
and
sorry, I'm
then-
messing up your planner there, but.
No, it's my homework from 2 weeks ago says it's as is due.
Okay. So I will see here. I've got these. I got to return them to you. So I'm able to try and return them right now, and then we'll see if I just didn't record it or whatever.